Hi everyone, welcome back to Math 251. Today's mathematician of the day is Émilie du Châtelet, who was an 18th century mathematician who created a translation and commentary on Newton's mathematical work on calculus. Her commentary on his work is considered vital to understanding his original manuscript. That is totally awesome. And the math history fact of the day is that the Aboriginal native peoples of Australia had base 4, 5, and 6 number systems, and they often used them in conjunction with one another. So here we only have one base number system, base 10. So it's pretty remarkable that they used 4, 5, and 6 number systems interchangeably. That's awesome. So last week we talked a bit about graphs, and today we're talking more about graphs, specifically what certain derivatives tell us about a graph. So when do we know if a graph is increasing or decreasing? We already know this. We've gone over this a couple of times, maybe not explicitly, but suppose a function f is defined on an interval I. We say that f is increasing on I if f of x2 is greater than f of x1 when x2 is greater than x1. This is just, as we know, increasing, just like that. That's an example of increasing. And we say that f is decreasing if f of x2 is less than f of x1 when x2 is greater than x1. So that's just any sort of decreasing function. So how do we know when a certain function is increasing or decreasing if we don't have the graph right in front of us? Well, luckily we have a theorem for that. Suppose f is continuous on an open interval I and differentiable at all interior points of I. If f prime of x is greater than 0, then f is increasing. And if f prime of x is less than 0, then f is decreasing on that interval. So in order to see if a function is increasing or decreasing, we simply need to take the derivative and see whether it's positive or negative. So let's sketch an example. Here in example 1, we want to sketch a graph of a function f that is continuous on all real numbers and satisfies the following conditions. So we want f prime of x to be greater than 0 from negative infinity to 0, 4 to 6, and 6 to infinity. So what does f prime of x is greater than 0 mean? We want our function to be increasing on all of these intervals. All right, we want f prime of x to be less than 0 from 0 to 4. That means that our function is decreasing on this interval. F prime of 0 is undefined. What does it mean for the derivative to be undefined? Well, we can either have an asymptote there, a hole there, or a corner here. However, we have to pay attention because in this particular example, we want f to be continuous on all real numbers. So if I have an asymptote or a hole, I won't be continuous, so I need to be a corner. And finally, f prime of 4 is equal to f prime of 6 is equal to 0. What does it mean when we have f prime of a number equal to 0? Well, as we learned last week, that means that we have critical points there. So maybe a max or a min. Maybe. All right, so we want to draw a function that has all of these features. There are lots of different ways to draw this particular graph. So let's see, I have 1, 2, 3, 4, 5, 6, we'll go up to 8. So the first thing is from negative infinity to 0, I am increasing. So if I have an arrow like this, I am increasing from 0 to infinity. I have to be careful at 0 because f prime of 0 is undefined. So I'm going to make a corner at the point 0. And then from 0 to 4, I am decreasing. So maybe I'll do something like this. Again, there are lots of different ways to draw this kind of graph. So I'm decreasing from 0 to 4. I'm increasing from 4 to 6. And I'm increasing from 6 to infinity. So what happens here at the point 6? Because we know that f prime of 4 is equal to f prime of 6 is equal to 0. So here at 6, this is a critical point, but it's not a max or min. We're going to talk about this here in a second, actually. But this is a critical point that's not a max or min. And then here at 4, we can see that this is a local min. All right, so let's double check our graph to make sure everything looks okay. So let's see, we have increasing from negative infinity to 0, that's good. From 4 to 6, also good. And from 6 to infinity, looks good there. We are decreasing from 0 to 4, we got that. F prime of 0 is undefined, that's true because we have a corner. And f prime of 4 is equal to 0, and f prime of 6 is equal to 0. Again, f prime of 6 is equal to 0 because I didn't draw it super great here, but if we drew a tangent line here, it would be horizontal. So that's how we know that we have a derivative equal to 0 there. All right, let's move on to an example where we have an equation. We want to find the intervals on which f of x equals x times e to the negative x is increasing and decreasing. So just to remind ourselves, our function is increasing when f prime of x is greater than 0 and decreasing when f prime of x is less than 0. So what I need to do here is figure out where my derivative is positive and where my derivative is negative. So first, obviously, I need to find the derivative. So to find the derivative of f of x equals x times e to the negative x, I'm going to have to use the product rule. So that gives us f prime of x is equal to the first times the derivative of the second, that is negative e to the negative x, plus the second times the derivative of the first. Okay, and then since I want to set this equal to 0, I'm going to factor as much as I can. So from both of these terms, I can factor out a e to the negative x. From that, I have left a negative x from the first term and a 1 from the second term. So I'm trying to find where f prime of x is greater than 0 and less than 0. So the first thing I'm going to do is see where they are equal to 0. And what are we finding here? Well, we're finding our critical points, right? Our critical points is when f of prime is equal to 0 or not defined. So I'm going to set this equal to 0. And now I see that I have two things multiplied together, e to the negative x and negative x plus 1. When I have two terms that are multiplied together and they equal 0, I know that one of them has to equal 0. But e to the negative x never equals 0. If we look at the graph, it just never does. So the only possibility I have is setting negative x plus 1 equal to 0, which gives me x equals 1. And this is our critical point. So once we've found our critical point, again, this is where f prime of x is equal to 0. This is how I solve this kind of problem. At my critical point, I know that it's definitely possible that I'm changing from increasing to decreasing or vice versa. So I need to check out what's going on around my critical point. So what I'm going to do is I'm going to draw a number line and I'm going to draw my critical point on here. In this case, I have 1. And I'm going to test on either side of 1. We can pick any number that we would like on either side of 1. The easiest case here on the left is just 0 and 2. But again, either number on either side works. And from here, I want to see if my derivative on the right side of 1 and on the left side of 1 is positive or negative. So I'm going to test f prime of 0. So if I put in 0 into my derivative, which is this guy right here, I get e to the 0 times 0 plus 1. And this is just equal to 1, which is a positive number. So this shows that at the point 0, my derivative is positive. So I'm going to write a positive sign here. Remember, that tells me that I am increasing here. And then I also am going to find f prime of 2, which is e to the negative 2 plus 1, which is negative e to the negative 2, which is negative. So that means that the derivative at the point 2 is negative, or that my function f is decreasing. These are the only 2 points that we need to test. Since I only have 1 critical point, that's the only possibility I have where my function is changing from increasing to decreasing. Remember, a critical point is often a local max or min. So, here I have a local max. Here I'm changing from increasing to decreasing. If I were to have a local min, here I'm changing from decreasing to increasing. So at our critical point, that's the only possibility I have for changing from increasing to decreasing, or vice versa. So what this number line tells me is that I am increasing from negative infinity to 1, since my derivative is positive there, and decreasing from 1 to infinity. Oops. That is what I can tell from this number line. What's happening at 1? Well, that is obviously our local max. So let's take a look at this function, x times e to the negative x on Desmos, just to see what is actually going on. Y equals x times e to the power of negative x. Whoops, negative x. There we go. So here is our function. And if we look at the point 1, that's right here. And we can see it's pretty slight, but it is a local max here, right? It starts to decrease after 1. We can see that more clearly over here. So I'm increasing from negative infinity to 1, and then I'm decreasing from 1 to infinity. That is what we see on this graph. So pretty cool that we can tell this just by taking the derivative, right? Okay. The next thing that we are going to talk about is called the first derivative test. So we're going to be using this a lot in the coming week or so. Assume f is continuous on an interval that contains a critical point c, and assume f is differentiable on an interval containing c, except perhaps at c itself. If f prime changes sign from positive to negative as x goes through c, then c is a local max. If f prime changes sign from negative to positive as x increases through c, then c is a local min. And if f prime does not change signs near c, then c isn't a local max or min. So we sort of already saw this in example 2, right? Here at the point, our critical point 1, I'm changing from increasing to decreasing. And even if I just draw a rough sketch of this, right, I'm changing from increasing to decreasing. So obviously that means that I have a local max at the point 1. So if we ever get confused about the first derivative test, we can just draw a picture of what's going on. and that will hopefully clarify it. Okay. Next we have a function 3x to the power 4 minus 4x to the power 3 minus 6x squared plus 12x plus 1. We want to find the intervals where this function is increasing and decreasing and find the local extrema. So increasing, remember, means f prime of x is greater than 0. Decreasing means f prime of x is less than 0. And the local extrema occurs when f prime of x is equal to 0. So, of course, here we are going to have to take the derivative. So, taking the derivative using the power rule gives me f prime of x equals 12x cubed minus 12x squared minus 12x plus 12. Lots of 12s. Well, obviously from here I can factor out a 12, right? So I'm left with x cubed minus x squared minus x plus 1. And I don't expect you to know how to do this factoring, but this does factor as 12 times x minus 1 squared times x plus 1. Again, I don't expect you to know how to do that, but that does factor just like that. And remember, this is f prime of x. So first, like I did in the previous example, I'm going to set this equal to 0 to find the critical points. So I have 0 equals all of this. Well, obviously 0 never equals 12. So if I set my x minus 1 squared term equal to 0, x minus 1 squared equals 0 gives me x equals 1. And if I have x plus 1 equals 0, I get x equals negative 1. So these are my two critical points. Now that I have my two critical points, I know that it's possible that I have a local max or min at either of these 2 points. So I need to employ my first derivative test to see if my derivative changes signs at x equals 1 or at x equals negative 1. So let's draw our number line here. I have my two critical points that I need to put on negative 1 and positive 1. I need to test each interval here. So I'm going to choose the number 0 here. I'm going to choose 2 here and negative 2 here. Now I need to plug in each of these numbers, negative 2, 0, and 2, into f prime to see if I am positive or negative there, if the derivative is positive or negative there. So I take f prime of negative 2. That is equal to 12 times negative 2 minus 1 squared times negative 2 plus 1. And let's see, anything squared is positive, so I have 12 times something positive times something negative, so this is negative. So I'm negative here. My f prime is negative. That means I'm decreasing there. Okay, f prime of 0 is equal to 12 times 0 minus 1 squared times 0 plus 1. This is anything squared is positive. I have 12 times something positive times 1, so that's positive. So from negative 1 to 1, I am increasing. And then f prime of 2 is 12 times 2 minus 1 squared times 2 plus 1, which is 12 times something positive times something positive, which is positive. So I see that I'm increasing from negative 1 to infinity, and I'm decreasing on negative infinity to negative 1. So let's write that down. Decreasing from negative infinity to negative 1 and increasing from negative 1 to infinity. And then what about my local extrema? Well, according to my first derivative test at the top of this page, if f prime changes signs, then I know that I have a local max or min. In this case, my derivative does change signs from negative to positive at negative 1. And according to our first derivative test, if I change from negative to positive, that means that c is a local min. So I have a local min at the point x equals negative 1. It is pretty amazing that we can figure out all this stuff about our graph. So let's take a look at this function. That might be helpful here. So if I graph the function, let's see, we have y equals 3x to the power 4 minus 4x cubed minus 6x squared plus 12x plus 1. I have y equals twice here. Okay, so here is our function in all of its glory. And we have a local min here at negative 1. We see that we're decreasing from negative infinity to negative 1. And then we're increasing from negative 1 to infinity. And then here is our point 1, which we found to be our other critical point. And something is going on there, right? I'm kind of, there's like a curve there. It kind of looks like a cubic function, doesn't it? It looks like the line y equals y cubed. So something is going on there, which is something else that we're going to talk about today. All right, next we have another theorem. One local extremum implies absolute extremum. So suppose f is continuous on an interval I that contains exactly one local extremum, max or min, at C. So if a local maximum occurs at C, then this means that the absolute max occurs at x equals C. And if a local minimum occurs at C, then the absolute minimum occurs at C. So basically, if I just have one local extremum, that means that it is the absolute extremum. Okay, on to what we are calling concavity and inflection points. So more definitions here. Okay, let f be differentiable on an open interval I. If f prime is increasing on I, then we say that f is concave up on I. I'll draw some pictures here in a second. If f prime is decreasing on I, then f is concave down on I. If f is continuous at C and f changes concavity at C, then we say that f has an inflection point at C. So we have another test here, test for concavity. So suppose that f double prime exists on an open interval I. Then if f double prime is greater than 0, then f is concave up. If f double prime is less than 0, then f is concave down. And if C is a point of I at which f double prime changes signs, then we call C an inflection point. So what the heck does all of this look like anyway? What does it mean for a function to be concave up or concave down? So let's draw a few pictures here of some different graphs. So what if I have something like this? Well, this here is my critical point, right? Because it's a local max or a local min. In this case, local max. Critical point. But this is what it means for a function to be concave down. In this particular example, our function is concave down the entire real line. So it looks like a function is concave down when it looks like an upside down U, basically. What about something like this? So here, we don't have a local max or a local min, right? Because we're going down forever and up forever. But still, this point right here is our critical point. If we took the derivative and set it equal to 0, we would find this as our critical point. And it's also our inflection point. That's because it changes concavity here. So from here on over, I am concave down because it kind of looks like one side of an upside down U. So here I'm concave down. And then over on this side of my critical / inflection point, this is what it looks like to be concave up. It looks like a right side up U. So this is concave up. So because I changed from concave down to concave up, that means that this critical point is also an inflection point. Okay, and then we could also have just a plain old concave up function as well. So this is what it means for a function to be concave up. This is our critical point, not an inflection point here since I'm not changing concavity. And it's concave up the whole time. So let's go back real quick and look at the example that we just did, example 3, because something weird was going on at the point x equals 1. So let's go back to this graph here from example 3. So we found 1 was our critical point, but we found also that there was not a local max or min at 1, which we can see pretty clearly on this graph, right? There's no local max or min at 1. However, what's happening here is 1 is an inflection point. Because our graph, let me zoom in here a little bit, from the left side here all the way until 1, our graph is concave down. If we ignore the part right of 1 real quick and we just look at the left side, we see that this kind of looks like half of an upside down U. So we're concave down there. And then to the right of 1, we are concave up. So that's why we got that 1 was a critical point, but not a local max or min. So here 1 is acting as an inflection point because we're changing from concave down to concave up. All right, let's do some examples with concavity. Example 4 says, find the intervals which the function f of x equals sine inverse of x is concave up or concave down on the interval from -1 to 1. So what does this mean? So concave up, just to remind ourselves, means that f double prime is greater than 0. Concave down means that f double prime is less than 0. Okay, so if I have f of x is equal to sine inverse of x, I want to find f double prime. So if f of x equals sine inverse of x, this means that f prime of x is equal to 1 over square root of 1 minus x squared. Another way of thinking about this is 1 minus x squared to the power of -1/2. So if I want to find f double prime here, I am going to have to use the chain rule. hold on one second. I think my dog is getting into something. Sorry about that. My dog is okay. All right, so we are going to have to use the chain rule here. So that means that my outer function f is x to the power of negative 1/2, and my inner function g is 1 minus x squared. This makes f prime equal to negative 1/2 x to the negative 3/2, and g prime equals negative 2x. So then, coming up here, f prime of g times g prime is equal to negative 1/2 1 minus x squared to the negative 3/2 times negative 2x, which is pretty ugly. But let's see, I'm going to combine this negative 1/2 with this negative 2. If I multiply those together, I just get 1. So I'm going to bring this x out in front. So I get x times 1 minus x squared to the negative 3/2. And another way to think about this, since I have that negative exponent, is I can move this guy to the denominator since I have a negative power there. And if I make that into the denominator, that makes my negative 3/2 positive. So I will just have this x on top. And then here on the bottom, I have 1 minus x squared to the power of 3/2. And remember, I want this to equal 0 because this is f double prime. So I'm going to do this number line test again, except in this case I will be working with f double prime since I'm dealing with concavity here. So this is my f double prime here, x over 1 minus x squared to the power of 3/2. So I'm going to, if I set this equal to 0, then this will be my critical point, possibly my inflection point, we'll see. And when does this function equal 0? Well, when I have a rational function and I set it equal to 0, that means that I need to set the top of my function equal to 0. So this makes my critical point x equals 0. Critical point / inflection point. So then I am going to make a number line again, and I'm going to include my critical point here, which is x equals 0. And I'm going to pick any point on either side of this. I'll pick 1 and negative 1. Oh, you know, I can't pick those, can I? Because that makes my denominator equal to 0. So let's pick 2 and negative 2. So again, I'm trying to find concavity. I need to put my points negative 2 and positive 2 into f double prime to see if f double prime of negative 2 is positive or negative, and f double prime of positive 2 is positive or negative. So if I say f double prime of negative 2, this is equal to, well, on the top of my fraction here, I will have a negative number, right? That's just x, negative over. And then here on the bottom, I have 1 minus x squared to the power of 3/2. So x squared here would be 4. So I'd have 1 minus 4 to the power of 3/2. And that is positive, because anything to the power of 3/2 here is positive. So I have negative over positive, which is negative. So I'm concave down from, dang, you know what? I can't use the points negative 2 and positive 2, can I? Sorry about that, because I'm on the interval from negative 1 to positive 1. It's all right. Okay, so let's pick some other points. I'm just having a hard time picking points here. Let's choose negative 1/2 and positive 1/2. 1/2. We will get the same results, but I do need to be careful to be in my interval. I'm just making sure y'all are paying attention. All right, so let's test again f double prime of negative 1/2. Again, we'll get negative on the top of our rational function, and then on the bottom we'll get 1 minus 1/4 to the power of 3/2, which is positive. So we still get negative here. So we are concave down from -1 to 0. And then what about f double prime of positive 1/2? Well, this would be positive on top. Over here we have, again, 1 minus 1/4 to the power of 3/2, which is positive. And this is overall positive. So we are changing from concave down to concave up at the point 0, which makes 0 an inflection point. But yes, we are concave, let's see, where am I going to write this? Concave down from -1 to 0, and up from 0 to 1. So let's graph this function to see what is going on here. So if I graph sine inverse of x, it doesn't look bad, does it? All right, this is what our function looks like. In fact, it's only defined from -1 to 1 here. So good thing I didn't actually put the points -2 and +2. So it's a little bit hard to see here, but if I look at the left side of 0 here, so from -1 to 0, that looks like part of an upside down U, which means that we're concave down here. And then if I look from 0 to +1, it's easiest to tell at the endpoints, but this is concave up as well. All right, we have one more theorem and one more example. Our next theorem is the second derivative test. It says, suppose f double prime is continuous on an open interval containing c with f prime of c equal to 0. So what does that mean? That means if f prime of c is equal to 0, that is a critical point. So if f double prime of c is greater than 0, this means that f has a local min at c. If f double prime at c is less than 0, that means f has a local max at x equals c. And if f double prime of c is equal to 0, then this test is inconclusive. So this is called the second derivative test. Earlier today we learned the first derivative tests, so we just have all sorts of tests that we are learning today. All right, so we want to use this second derivative test to locate the local extrema of the function f of x equals sine squared of x. So in order to find the first and second derivatives, well, to find the first one, we are going to have to use the chain rule. So that makes our outer function f equal to x squared, and our inner function g equal to sine of x. That makes f prime equal to 2x, and g prime equal to cosine x. So then f prime of g times g prime is equal to 2 sine x cosine x. And this is the first derivative, y prime. So then to find the second derivative, I am going to need to use the product rule here. But you know what? Nah, we'll just use the product rule. So the product rule tells me I'm going to have my first function 2 sine of x and my second function cosine of x, that means f prime will equal 2 cosine of x, and g prime will equal negative sine of x. So I get y double prime is what I have now, is the first 2 sine of x times the derivative of the second, negative sine of x, plus the second cosine x times the derivative of the first. Oops, 2 cosine x. So this will be negative 2 sine squared x plus 2 cosine squared x. I can factor a 2 out of each of these terms. So I'll be left with negative sine squared of x plus cosine squared of x. Now this looks really similar. This negative sine squared of x plus cosine squared of x almost looks like our Pythagorean identity for sine and cosine, the one that says sine squared of x plus cosine squared of x is equal to 1. And it's not quite that, but this is another identity. I don't expect you to know this, and if you were to be asked to use this on an exam, it would be given to you. But negative sine squared of x plus cosine squared of x is equal to cosine of 2x. So here we have y double prime is equal to 2 cosine of 2x. So next, now that I have my second derivative, I'm using the second derivative test here, so I need to set this equal to 0. Actually first I need to find, so according to my second derivative test, I need to find f prime of c is equal to 0. So I first need to set the first derivative equal to 0. So to find critical points, I set f prime of x equal to 0. So in this case, our f prime was 2 sine x times cosine x, and this is equal to 0. So here I have two functions that are being multiplied together, sine of x and cosine of x. So I need to see where each of them individually are equal to 0. So sine x equals 0. When? Well, sine x equals 0 at any time I have 0 pi, pi, 2 pi, 3 pi, 4 pi. So all of the pi's. I'm going to write this at x equals k times pi, where k is an integer. At any multiple of pi, sine of x is equal to 0. And what about cosine of x? Cosine of x is equal to 0 at pi over 2, 3 pi over 2, and continuing on. So I'm going to say x is equal to pi over 2 plus k pi, where k is an integer. So basically, every 1/2 pi, we have this function 2 sine x cosine x is equal to 0. That is what is going on here. So our critical points, if I summarize both of these up, pi k and pi over 2 plus pi k, I can combine these both into pi over 2k, since basically I have a critical point at every pi over 2. Where k is an integer, these are my critical points. So now to see if I have a local max or local min at these critical points, I need to apply the second derivative test. So I'm going to apply f double prime, and I'm going to test some values of k here. So if k is equal to 0, then I get a critical point of 0. So f double prime of 0 is equal to 2 cosine of 2 times 0 or just 2 cosine of 0, and this is 2, which is positive. So that means at 0, I have a local min. That's what this means. And then let's test the next pi over 2. So if k is equal to 1, then I'm going to say f double prime of pi over 2 is equal to 2 cosine of 2 times pi over 2, which is 2 cosine of pi. Cosine of pi is equal to -1, so this is -2, which is negative. That makes this a local max according to the second derivative test. And if I were to test a few more of these k values, what I would find is every integer of pi, so 0, pi, 2 pi, 3 pi, I would have a local min, and all of the alternating ones, so like pi over 2, 3 pi over 2, 5 pi over 2, etc., those are all local maxes. So I'm going to write this as local max at pi over 2 plus pi k, where k is an integer. So that's pi over 2, 3 pi over 2, 5 pi over 2, all of those. And I have local mins at pi k. So every pi's. If you don't believe me on this, feel free to test more values here in our second derivative test, but this is what you'll find. Whew. So we learned a lot today. We learned a lot of different theorems, a lot of definitions, and new words. So I do encourage you to go back through your notes and note any questions that you have about this lecture. I'd be happy to answer them. But other than that, I will see you all on Wednesday. Have a wonderful day.